Hi, welcome my neighbors. Today I'm starting up a new mini-series about electronics, and in particular about capacitors and inductors. The reason why I want to talk about this is because inductors and capacitors are basic components which you'll find common in many circuits. And if you want to build anything, you'd likely need to use them, especially signal processing and making filters out of them. So let's get into it. So just before we begin, just a couple of words on why I'm teaching basic electronics like capacitors and inductors, transistors and whatnot. Well, just in case the world ends, as you can see there, I hope you have the knowledge to build things out of junk parts, because these base components are in every electronics, and if you can scrap things together, all the power to you. Joking aside, though, the reason why I wanted to teach these things is because electronics has always been a hobby of mine, and by teaching it, it actually reaffirms my own knowledge. I do the necessary research to tell you things that are true. I'm not just going to tell you things that are lies or crap or just what I think it is, right? I actually do the research to be able to show you how these things really work, right? To the best of my knowledge anyways. So, and as well, I'd just like to kind of say that in today's world, these basic electronics are quite low tech. I mean, these are as basic as you can get, these components. But on the other hand, not everybody knows about them or understands them. And I think today it is actually quite sad that not everybody knows these things, right? We take this technology for granted. You know, we have high tech, we have AI these days, but are we actually advancing ourselves? That's the question, right? We keep building machines and building things, but do we know these things, right? Are we advancing our own knowledge, or are we giving that away to the computers? So anyways, that's just a quick little message. So let's get into it. Now, as part of this series, at the end of the series, I should say, we're going to be building a circuit that uses inductors. Now, I'm not going to give away what we're going to make, but let me tell you this. In order for us to build that circuit, we're going to have to learn about capacitors and inductors. So let's start with the simpler one first, in my opinion, which is capacitors. And you've probably seen these components. Now, a capacitor is characterized by two things. One, its capacity to store a charge or energy. And the other one is its ability to let through alternating currents and block direct currents. So this is a capacitor drawn in a circuit. Basically, this piece here is the capacitor. Basically, has two plates separated by an air gap. Here we have a battery. It's showing that this is connected. And what happens is, as the normal flow of electrons through the circuit, it comes around like this, right? But in the case of when you have a capacitor in between, the electrons don't actually cross the gap here. Okay, this circuit is actually kind of open. So what happens is that the electrons travel from the negative end of the battery, and when it gets here, something special happens. Because these plates are in such close proximity to each other, the electromagnetic field can actually I guess you can say they can be felt from across the gap. So while the negative electrons try to go over to the positive side of the battery, because there's a pole, you can imagine that there's like a pole there, right? And the force, actually what happens is, as these electrons get attracted to here, it cannot actually physically cross the gap. They get collected on this side. So if you can imagine, as time goes by, I can collect more and more and more and more electrons to a certain extent, because as long as there's depends on the voltage being applied to the capacitor. The more voltage, the more negative charge there can be here on the bottom plate. But at the same time, because there's so much negative charge, there is a lot of there's going to be a buildup of electromagnetic force here. And what happens is that on this side of the plate, electrons can be pushed out, and they go this way back into the battery, right? So if you can imagine, what happens when the atoms on this plate have lost their electrons? Well, if they've lost their electrons, then basically their overall charge is positive here, right? There's overall is a positive charge on here, right? And what ends up happening is that, given the same amount of voltage, or the same kind of force that you have here, the same pressure that's being applied to the plate, what happens is that these negative electrons will actually impede following electrons to come in. So as the more buildup there is electrons, the harder it is for more electrons to go there. So eventually the current stops entirely. Okay? In fact, the rapid charge and the eventually slowing down of charging of this capacitor can be characterized by this formula here. Okay? So basically what this formula says, it takes 5 times the resistance in the circuit multiplied by the capacitance of the capacitor. That's the amount of seconds it takes to fully charge a capacitor. And it doesn't matter how much voltage you put at it, right? Given a constant voltage, this is the amount of time it takes to charge. And if you can see, maybe later I can put it on the oscilloscope. Basically, at the beginning, when you first connect the circuit, the capacitor will actually rapidly charge. But you will see that as the charge increases, as time goes by, it actually takes more and more time for it to finish charging. Because, again, as I said, because this here, negative charge building up, it actually impedes the amount of electrons that can actually go onto that plate. So capacitors are measured, the capacitance is measured in a unit called farads. And that basically what that means is, different capacitors, there's different sizes, different capacities, and that's called capacitance, right? So if you can imagine, if I build a capacitor, each capacitor, if the surface area, or there's the plates across them are larger, then they can store more electrical charge. That's essentially what different sizes of capacitance actually means. What I want to show here with the diagrams on the top and bottom is that capacitors also have another property, which is, number one, given a DC current or a DC voltage being applied to the capacitor here, eventually, very quickly, it will block all the current flowing through it. Okay, there is a slight current movement when the capacitor is being charged, but as soon as it's finished charging, it becomes stopped. The DC current doesn't flow anymore, right? Now, interesting, the other property of it is, alternating currents, as you can see in the bottom, can flow through the capacitor. When you charge a capacitor using a constant voltage, as I mentioned before, as electrons collect on this plate, for example, here, generating an overall negative charge on this plate, what I mentioned was that you will no longer charge anymore, okay? Because the negative, in terms of the charge, is overall negative. And because it's negative, the electrons can no longer get pushed over to this side. Now that's under a constant voltage. If you ever experimented with capacitors, you know that if you apply a higher voltage later, you can always force more electrons onto this plate, and thus you can actually force more negative charge onto that plate. And that's exactly why capacitors will let through alternating currents, because an alternating current is basically a fluctuation, an up and down, you could say, in voltage. So even if I'm at the maximum capacity of electrical charge on this plate at a current given point in time, if I increase the voltage, then I will be able to put more electrons there. If I decrease the voltage, then the electrons can move back. It depends on how much electrical force is being put onto it. And with an alternating current, because it's changing, I could put more electrons there, or I could put less electrons there. And therefore, that's why capacitors can actually let through electrical current when it's alternating. And if you're wondering, when the capacitor is charging under a direct current, is there current flowing through? Yes, there is. The current does flow. If you give it a direct current here, as the capacitor is charging, the current does flow through. Okay, this is because before the charges all build up here, each time a certain amount of electrons move over to this plate, it is, again, there's an electromotive force here. It's forcing an electron to move off this plate, going in this direction. So as it's charging, yes, current will flow, but it will stop. When it's reached to its capacity, it will stop, right? So I thought, now that we learned a little bit about capacitors, let's build a circuit to prove what we learned, okay? So I thought maybe we can create a circuit like this, just a simple resistor and a capacitor connected like this to a battery. And what we can try to do is apply the formula we know. The amount of time it takes to charge a capacitor is 5 times the resistance times the capacitance, right? So if this is true, then even if I don't know what the capacitance is, as long as I know the two other variables in this equation, which is the resistance and the time, then I know how I can solve for how large the capacitance is on the circuit. So basically, if we rewrite this in a different way, given that we want to find the C like this, so when this formula is rewritten this way, just by using basic algebra, we take the 5 times the R and divide both sides by it, we get TS divided by 5 times R is equal to capacitance. So what we do, we measure the time it takes for the capacitor to reach its full charge. So if we're applying a constant voltage of, let's say, 5 volts to the capacitor at this battery through the resistor, if we say 5 volts, and we measured how long it takes to charge this capacitor to its limit, which is 5 volts, then we can plug it into these, plug that number into here and solve for the capacitance. So let's go and do that. So check this setup. I have now a power supply and the negative end connected to the negative end of the capacitor, and I have the probe connected to basically the positive in the capacitor. The resistor, this is a 100k resistor, 100k ohms, and I have another probe attached to this power supply. Now the power supply isn't connected yet, and I've set it up to be 5 volts here, as you can see there, right? So as soon as I connect the power, we'll be able to see on the oscilloscope the rise of the voltage. So as soon as I click it now, we can measure how much voltage, how long it takes for the voltage to rise. So I'm going to connect it right here in 3, 2, 1, go. So just so you can see, the yellow is the supply voltage. It's constantly at about 5 volts. So now the capacitor is rapidly charging, and now it's evening out. It's reaching the top, and we can see, I think due to some losses, it's probably not going to reach the top there. So let's just pause it here. I think it's never going to reach the top. And I think it's essentially finished charging. Let's give it a pause here. Yeah, it's never going to reach the top. So this is the reality with these circuits. Could be some losses, or maybe some inductance causing it not to fully charge. But let's pause it here. So guys, I was able to get it to pause. That was the button. I just wasn't paying attention. So behind the camera, it's kind of hard to see because I'm looking in front of my phone camera here. It's very small. But anyways, I can set my guide rules up to here, and I think so. The beginning line here, this dotted line here, I can set it to the beginning of where we plugged it in, and that's right here. And the ending line, this line here, which you can see on the screen, if you can see down there, it's actually being able to measure the this end line, sorry, it's being able to measure the delta seconds. So if I set it back here at the beginning, it's basically 0 seconds, right? So if I move it up and I set it to a place where approximately, I think it's finished charging, there's some losses in here, so it never reaches the top. It will never reach the top. So let's just say, let's put the line right here. Okay, so 4.52 volts is the maximum charge that this capacitor will hold. Will actually take. And I'll take the line, let's do a cross right here. So somewhere about, I'd say here, it's done charging, right? So this looks like, well, you know what? Actually, this looks like a more solid line. Let's take this, okay? So at this point, I think this is about finished, the charging. Well, you know what? The green line down here, some of it says, what's the V top, channel 1, V max 6464. So let's take, you know, is that significantly higher? No, not 64. Somewhere there. I don't know. It looks like it's about here anyways, right? So about, let's say, I don't know, put it here, 23 seconds or so, right? We've been into the maximum charge. So let's take that. Let's see how accurate our calculations is. So let's go to the math. So we said we're going to take the capacitance would be equal to the number of seconds. So this is approximately, we'll take it as 23.8 seconds, okay? So we put 23.8 seconds divided by 5 times the resistance, so it's 100,000 ohms, the resistance, and we'll close out brackets, right? And that should be our capacitance. So what we says here is that our capacitance is 0.000476 farads. Okay, so let's check it out. So most of the, they don't write these on the resistors, right? Like they don't write 0.00. It's usually in the closest units, right? So that the number is convenient for you to see. So at this level, let's just times it by a million, okay, and call it a microfarad, okay. 1, 4, 5, 6, okay. So according to our calculations, we have 47.6 microfarads. And let's take a look at the resistor itself. Okay. So I'll put away my power supply. If we can only get it to focus now. Let's take a look at this. Oh, do you see there? 47 microfarads. That's exactly what we got. We got 47.6. So this is a pretty good method, right? Provided that, when you look at it, there are some losses here. It doesn't get fully charged. And you can see, as long as you put the guidelines correctly, when it's about to be completed, that you set the line there. So it does work. This is great. So let's try it with another capacitor, unknown capacitor. Now I know this one's a lot smaller, so let's see. I've changed my time bases, and let's see if the experiment works. So I'm going to connect it. 3, 2, 1, go. And there we go. So the oscilloscope, I set it on capture mode. So the trigger will rise when the image will basically capture when we hit the specified voltage level. And look at this. Let's do some measurements now. So let's put the ruler here, the beginning marker, right on this yellow line. And once again, let's set our line to the maximum charge about here. And this line, let's do measurement. I think it reached the top probably about here, or a little higher. I don't know, but about here, let's say 5.2 volts. And probably reached about here, right? So it's close enough. Let's use this number. So it charged to maximum in about 180 milliseconds. So let's take that as a calculation. So go back to a calculator. So 180 milliseconds, 180, right? Divide by 1,000. Sorry, back. So 0.18 seconds, right? Divided by 5 times 100,000. Okay. Equals a very small number, but let's times it by a million to get the microfarad. So 0.36 microfarads. Let's take a look at what's on the capacitor. Oh, I see that this on the label. Let's see if we can see this. No, this is 50 volts. And the printing is very small on this. Oh, there it is. There it is. I think I see it. Sorry about this. There we go. 0.47 microfarads. So we're a bit off, but that's to be expected. I guess this is not a very accurate way of capturing it. Some losses or some guesses here too, right? So maybe let's take a look back in here at this image. Look at it carefully. So if we took this line and it's probably out here, so let's take it to the max, right? V64 is the max. If I took this line to 64, 60 or something like that here, and where this line actually crosses somewhere here, you know, bump it up to maybe 240 milliseconds, around that 244 milliseconds. If we redo the calculation, plug those numbers in, actually let's do it the other way. Let's give it the actual numbers. So 0.47 divided by 1 million to make it the micros, right, times 5 times 100,000. What does that give us? 0.235 seconds. By the calculation, it should put 0.35 seconds to charge this capacitor. And our line here, okay, I mean, we're in the ballpark, right? 244 milliseconds down here is where it says. So we're pretty close. We're pretty close. This is not the most accurate way, but it was just an interesting experiment to see at least if our understanding is right. So, in conclusion, what did we learn today? Well, we learned that capacitors store charge. Different capacitors have different size. Different size are called capacitances, right? We also learned that the capacitors block DC current and allow alternating currents to pass through. We learned that also the time it takes for a capacitor to build up charge is directly related to its capacitance and the resistance on the circuit, multiplied by 5. All right. And we also learned, you know, on the practical examples that, you know, depending on the resistance you choose on the resistor, you may not be able to fully charge a capacitor, simply because I chose a really, really high 100k ohm resistor, and what it's telling me when we're charging this on the experiment is that, well, if the input voltage is still 5 volts and the capacitor is only reaching about 4.6 volts, that means the resistor is dropping the remainder of the voltage. And what does that mean? Well, it means there's a current flowing through. And the reason why there's a current is because there's a loss in the capacitor. Somewhere the charge is being lost. This is not a perfect world, and therefore you know, the capacitor cannot hold its charge. Now, if it really held its charge perfectly, then you would expect the final result is that the capacitor would be charged fully to 5 volts. But like again I said, because I chose such a high resistor, it's actually taking a long time for the capacitor to charge. So much time, in fact, that it's losing its charge, right? So we'll never get to 5 volts. So that's where I'd like to end off this video today. It's getting a pretty long video and probably losing your attention. Now, the next video, we're going to do something really fun. We're going to be looking at how the capacitor deals with alternating current, and we'll be devising an experiment to demonstrate that as well. So if you like this video, please like and subscribe, and wait for the next one. It's going to be exciting. We're going to see alternating currents traveling through the capacitor, and we're going to devise another way to measure the size of the capacitor, its capacitance, by using an alternating current. So stay tuned and have a nice day.